Before we can jump into our hypothesis test for a difference of means, we need to establish a few basics about the sampling distribution for a difference of means. We have a formula for standard error, but much like the formulas that we saw for two proportions or for a difference of proportions, we are not responsible for it. You don't have to use this formula to calculate standard error. On homework, you can use the applet, and on tests, the standard error will be provided anytime we're talking about a difference between two means. We have an estimate of degrees of freedom, which is very similar to our degrees of freedom for one mean. Again, we're going with this idea of n minus 1, except we have two different samples and each one of them has an n. So what we do is we say it's a reasonably conservative estimate of our degrees of freedom to take the n from the smaller sample. So that we look at our two n's, whichever is smaller, we just take that smaller n and then subtract 1. There is a formula that gets us a better estimate of degrees of freedom that is very messy and complicated. It's based on this Satterthwaite approximation idea, but we figure that if you want more accuracy, you can use software to get a better estimate of your degrees of freedom, and we don't touch that formula in this course. So anytime we're doing something by hand, our degrees of freedom are just based on the smaller sample. It's going to give you a smaller value of degrees of freedom than the other formula would give you, and we call that a conservative estimate because it's going to make your p-values bigger and it's going to make your margins of error on your confidence intervals bigger, so that we're still safe in our conclusions anytime we are concluding that we would reject the null hypothesis. It just makes it a little bit harder to reject. Following again on our ideas from one mean, we have sample size conditions for using the t-distribution. This is the same rule of thumb that we established for one mean, and now it has to hold for both values of n. So this must hold for both n1 and n2. So if either of those sample sizes is smaller than 30, then we want to look at the shape of that distribution. So with these things in mind, we'll go ahead and venture off into our first hypothesis test. A t-statistic is calculated, again, based on this same model of sample statistic minus null parameter or null value divided by standard error. Our sample statistic, anytime we're talking about a difference between two means, is the difference between the two sample means. So x1 bar minus x2 bar. And our null value, what we would set this equal to, mu1 minus mu2 equal to under the null hypothesis, is going to be 0. And so this gets us a very nice, concise formula for our t-statistic. Going into an example, the nutrition study dataset includes patients that are undergoing elective surgery to remove a non-cancerous lesion. We can't necessarily assume that this is representative of all adults in the US, so we will just assume that any inference we do is subject to a kind of hypothetical population of people who would be going under this similar kind of surgery. We're going to perform a test of hypothesis to address the question of whether Quetelet, which is a fancy name for BMI, body mass index, named after, I believe, the French individual who defined it, differs among smokers and non-smokers among individuals in this population. So what type of variables do we have, first of all? That Quetelet body mass index is a quantitative measure that is based on height and weight. So it's a quantitative measure of one's weight in proportion to one's height. So this is quantitative. And the variable smoke, which would have yes and no, or smoker and non-smoker as its values, is categorical. So we do have the correct kind of data for addressing a question about a difference of means. Remember, it's not two quantitative variables, it's one quantitative variable because we need to make sure that we are comparing means of the same quantitative measure, and the categorical variable is what defines the grouping. So the categorical variable really can only have two different values for this kind of situation. So we need to go to descriptive statistics for one quantitative and one categorical variable in StatKey. So let's go ahead and open that nutrition study dataset. Here in StatKey, under descriptive statistics and graphs, I'm going to one quantitative and one categorical variable. And I'm going to upload file. I'm going to sort these by name and scroll down to the ends to find nutritionstudy.csv. Kettle is my quantitative variable, smoke is my categorical variable, and I can see these two distributions now. They do look like they have a bit of right skew, right? Quite a bit. They look similarly shaped, and they look even not that far off from each other, so it's not that clear we're going to see a difference here. And also coming up to our sample sizes, we see they're both greater than 30, so that should be able to handle some amount of skew in our population or in our sample as we go into the t-distribution. Now what we're going to do is write down the values for sample size, mean, and standard deviation, leaving out these overall values, just going for the no and yes in our notes. And I'll choose to just follow the same order in which they showed up in StatKey and say that these go with my no and these go with my yes. We definitely need to keep track of that. So my sample size for no is 272, a lot more non-smokers than smokers. The mean BMI is 26.389. And my standard deviation is 6.145. The sample size for my smokers is much smaller at 43. Mean is 24.695. And standard deviation 4.915. So right away we can see that at least in our sample, the mean BMI actually appears to be a little bit lower among smokers than among non-smokers. My hypotheses, null hypothesis, is that the two means are the same, but now we're talking about population means, so we never write the hypotheses in terms of x bar. This is going to be mu sub n equals mu sub y. And my alternative hypothesis, remember the question was, is there any difference in BMI among smokers and non-smokers? I want a two-sided alternative hypothesis here. Makes things a little bit easier. We don't have to be too concerned about what direction we're going. So we have a two-tailed test. Also remember that each of these hypotheses can be written in terms of a difference of parameters. Mu sub n minus mu sub y equals 0. Mu sub n minus mu sub y is not equal to 0. This is often really necessary to do if you have a one-tail test, just to make sure you stay very consistent about everything. With a two-tail test, you can afford to be a little bit less careful. Okay, so our sample statistic is xn bar minus xy bar. I'm staying in the same order that I subtracted my parameters here, and that is going to be 26.389 minus 24.695, which turns out to be 1.694. The correct degrees of freedom, I can see of my two ends up here, I have a 272 and I have a 43. I'm going to choose the smaller of the two and subtract 1 to get 42 degrees of freedom. It's okay to go ahead and just choose in Table A the closest line. So we'll use 40 when we get to table A, because there isn't a line corresponding to 42, it's okay to be conservative and go down a little bit. It's also okay to just take whatever's closest. We're not that concerned because it only differs in the thousandths place. So when we get to table A, we'll just use the row corresponding to 40 degrees of freedom. And the standard error applet, we're going to look up in Blackboard in order to calculate the standard error. Just like with difference between two proportions, there's a direct link in the section corresponding to this material. So if I click on this standard error applet link, it takes me exactly where I want to go. Or if I'm out of this context and just want to get to a standard error calculator, way down here under external links, this gets me to a more general map, and I would look for SE for the difference of sample means from independent samples, and click on that. This gets me to the same place ultimately. So I'm going to enter my standard deviation and sample size from both of my samples. Sample 1 has a standard deviation of 6.145. Remember that we don't actually use the means here at all. The standard error estimate is only based on spread and sample size. So don't get mixed up between your standard deviation and your mean. 4.915 for my standard deviation and 43 for my sample size. And compute standard error. You can see we get the precise degrees of freedom here. That's based on that Satterthwaite formula I was talking about. You don't have to use these, but if you ever want to at some point in the future, you certainly can. The smaller of the two, n-1, will be sufficient for everything we do. And our standard error estimate is 0.8370. All right, so our t-statistic, recalling this nice formula, is our sample statistic of 1.694 divided by the standard error of 0.837, and that gets us 2.024. At this stage, we're prepared to draw a rough sketch of a bell-shaped curve to represent our t-distribution, centered at 0, and mark our t-statistic on the curve. 2.024 would be getting into the tail, but not very far into the tail. So I'll put it here where we can definitely still see some tail area beyond it. And shade in the appropriate tail. This is a two-sided alternative hypothesis looking back up at our HA, and therefore we want a two-tailed test, so I'm going to fill in this right tail and an approximately symmetric left tail over here as well. Let's go to StatKey now and find our p-value. We're going to theoretical distributions, t, and we decided we needed a t-distribution with 42 degrees of freedom. I will hit two-tail because I have a two-tailed p-value and overwrite this boundary value of 2.018 with my calculated value of 2.042. Or rather, 2.024 is the correct value. This gives me, it looks like a p-value of, we have 0.025 in each tail, so when we add those two together, we get a p-value of exactly 0.05, not exactly, but at least two decimal places equal to 0.05, which is not very common for that to come out precisely at our most common significance level. So our p-value here is equal to 0.05, and now we need to write a conclusion. A p-value very close to 0.05 we generally describe as moderate evidence, so we're going to say that we have moderate evidence and then try to describe our alternative hypothesis in context. So we always have evidence for the alternative hypothesis. In this case, the alternative hypothesis is that these two means are not equal, where the meaning of these is the mean Quetelet index, or BMI, between non-smokers and smokers. So we have moderate evidence that these are not equal, meaning that there is a difference in mean Quetelet index among smokers and non-smokers. So this is a two-sided alternative hypothesis. The alternative hypothesis is only that there is some difference, but we can tell from our sample statistics which one is higher. We can actually see that the mean Quetelet index turns out to be higher among the non-smokers. Generally, we consider not smoking to be associated with healthier outcomes, and we consider lower BMI to be healthier, but those aren't absolute truths, right? It's not always true that a lower BMI is necessarily healthier. So we actually do see a lower BMI on average with our smokers, so we can also remark on that in our conclusion. So again, our full conclusion has a description of the strength of evidence and a verbal description of what it means for the alternative hypothesis to be true, that the mean Quetelet index differs between smokers and non-smokers, and if we had a two-sided alternative hypothesis and we did get some sort of statistically significant evidence for that alternative hypothesis, it's best to also include a statement indicating the direction.